Learning objectives. In this lesson, you will be learning about graphs and the following in detail. Graph representation, traversal schemes, spanning tree, shortest path algorithm, primes and kruskals. Graph representation. Introduction. Hi, welcome. Now we're going to see about graphs and its representation. A graph is a finite set of nodes with edges between nodes. For graphs to be computationally useful, they have to be conveniently represented in programs. There are two computer representations of graphs: adjacency matrix, adjacency list. Adjacency matrix. Let's see what is an adjacency matrix, and the definition goes like this. An adjacency matrix is a matrix which describes a graph by representing which vertices are adjacent to which other vertices. A representation of a directed graph with n vertices using n multiplied by n matrix, where the entry at ij is 1, if there is an edge from vertex I to vertex j. Otherwise, the entry is 0. A weighted graph may be represented using the weight as the entry. An undirected graph may be represented using the same entry in both ij and ji, or using an upper triangular matrix. Each cell A of I, j of an adjacency matrix contains 0. If there is an edge between ith and jth vertices and 1 otherwise. Before discussing the advantages and disadvantages of this kind of representation. Advantages. Adjacency matrix is very convenient to work with. Add or remove an edge can be done in O of 1 time. The same time is required to check if there is an edge between two vertices. Also, it is very simple to program, and in all our graph tutorials we are going to work with this kind of representation. Disadvantages. Adjacency matrix consumes huge amount of memory for storing big graphs. All graphs can be divided into two categories: sparse and dense graphs. Sparse ones contain not much edges. Number of edges is much less. The square of number of vertices, E, lesser than V of 2. On the other hand, dense graphs contain number of edges comparable with square of number of vertices. Adjacency matrix is optimal for dense graphs, but for sparse ones, it is superfluous. The next drawback of the adjacency matrix is that in many algorithms, you need to know the edges adjacent to the current vertex. To draw out such an information from the adjacency matrix, you have to scan over the corresponding row, which results in O of V complexity. For the algorithms like DFS or based on it, use of the adjacency matrix results in overall complexity of O of V of 2, while it can be reduced to O of V plus E when using adjacency list. The last disadvantage we want to draw your attention to is that adjacency matrix requires huge efforts for adding, removing a vertex. In case a graph is used for analysis only, it is not necessary. But if you want to construct fully dynamic structure using of adjacency matrix, make it quite slow for big graphs. To sum up, adjacency matrix is a good solution for dense graphs, which implies having constant number of vertices. This is how we compute the matrix for the given graph. Let's look at yet another example with a different scenario. Find the graph and its respective graph. For vertex which doesn't have edges. Program for adjacency matrix. Adjacency list. This kind of the graph representation is one of the alternatives to adjacency matrix. It requires less amount of memory and in particular situations even can outperform adjacency matrix. For every vertex, adjacency list stores a list of vertices which are adjacent to current one. Advantages. Adjacent list allows us to store graph in more compact form than adjacency matrix, but the difference decreasing as a graph becomes denser. The next advantage is that adjacent list allows to get the list of adjacent vertices in O of one time, which is big advantage for some algorithms. Disadvantages. Adding or removing an edge to or from adjacent list is not so easy as for adjacent matrix. Adjacent list doesn't allow us to make an efficient implementation if dynamically change of vertices number is required. Adding new vertex can be done in O of V, but removal results in O of E complexity. To sum up, adjacency list is a good solution for sparse graphs and lets us change the number of vertices more efficiently than using an adjacent matrix. But still, there are better solutions to store fully dynamic graphs. Traversal schemes. Traversing a graph is similar to traversing a binary tree. A graph might have cycles, might not be able to traverse the entire graph from a single vertex. Most common graph traversal algorithms: depth-first traversal and breadth-first traversal. Depth-first search. Depth-first search definition. Depth-first search (DFS) is an algorithm for traversing or searching tree or graph data structures. One starts at the root, selecting some arbitrary node as the root in the case of a graph, and explores as far as possible along each branch before backtracking. A depth-first search explores a path all the way to a leaf before backtracking and exploring another path. For example, after searching A, then B, then D, the search backtracks and tries another path from B. Nodes are explored in the order A, B, D, E, H, L, M, N, I, O, P, C, F, G, J, K, Q. N will be found before J. Depth-first traversal. Depth-first traversal at a given node V. Mark node V as visited. Visit the node. For each vertex U adjacent to V. If U is not visited, start the depth-first traversal at U. DFS follows the following rules. Select an unvisited node X, visit it, and treat as the current node. Find an unvisited neighbor of the current node, visit it, and make it the new current node. If the current node has no unvisited neighbors, backtrack to the parent and make that parent the new current node. Repeat steps 3 and 4 until no more nodes can be visited. If there are still unvisited nodes, repeat from step 1. Breadth-first search. Breadth-first search (BFS) is a strategy for searching in a graph when search is limited to essentially two operations. A. Visit and inspect a node of a graph. B. Gain access to visit the nodes that neighbor the currently visited node. The BFS begins at a root node and inspects all the neighboring nodes. Then for each of those neighboring nodes in turn, it inspects the neighbor nodes which were unvisited and so on. Spanning tree definition. A tree is a connected undirected graph with no cycles. It is a spanning tree of a graph G if it spans G, that is, it includes every vertex of G, and is a subgraph of G. Every edge in the tree belongs to G. A spanning tree of a connected graph G can also be defined as a maximal set of edges of G that contains no cycle, or as a minimal set of edges that contain all vertices. Spanning tree. Suppose you have a connected undirected graph. Connected. Every node is reachable from every other node. undirected. Edges do not have an associated direction. Then, a spanning tree of the graph is a connected subgraph in which there are no cycles. Total of 16 different spanning trees for the graph. The minimum spanning tree for a given graph is the spanning tree of minimum cost for that graph. Minimum weight spanning tree, MST. On a weighted graph, a MST connects all vertices through edges with least weights. Has W of t lesser than or equal to W of t for every other spanning tree t in G. Adding one edge not in MST will create a cycle. Finding minimum spanning tree. Algorithms, Kruskal's and primes. AD and CE are the shortest edges with length 5. AD and CE has been arbitrarily chosen, so it is highlighted. CE is now the shortest edge that does not form a cycle with length 5, so it is highlighted as the second edge. The next edge, DF, with length 6 is highlighted using much the same method. The next shortest edges are AB and BE, both with length 7. AB is chosen arbitrarily and is highlighted. The edge BD has been highlighted in red because there already exists a path in green between B and D, so it would form a cycle ABD if it were chosen. The process continues to highlight the next smallest edge, BE with length 7. Many more edges are highlighted in red at this stage. BC because it would form the loop BCE, DE because it would form the loop DEBA, and FE because it would form FEBAD. Finally, the process finishes with the edge EG of length 9 and the minimum spanning tree is found. Let us look at another example so closely. Remember, edge first. 1. Arrange all edges in a list L in non-decreasing order. 2. Select edges from L and include that in set T. Avoid cycle. 3. Repeat 3 until T becomes a tree that covers all vertices. Start from any arbitrary vertex. Find the edge that has minimum weight from all known vertices. Stop when the tree covers all vertices. Let's choose 2, 7 at this moment. We are free to choose 5, 8 or 6, 7, but not 7, 8 because we need to avoid cycle. Let's choose 5, 8 at this moment. The best is now choose 4, 5. The best now is to choose 4, 3. The best now is to choose 3, 6 or 5, 6. A MST is formed. Merge sort. Merge sort is a recursive algorithm that continually splits a list in half. If the list is empty or has one item, it is sorted by definition. If the list has more than one item, we split the list and recursively invoke a merge sort on both halves. Once the two halves are sorted, the fundamental operation called a merge is performed. Merging is the process of taking two smaller and sorted lists and combining them together into a single. Merge algorithm. The following steps show how merge sort works. Introduce read indices I, J to traverse arrays A and B accordingly. Introduce write index K to store position of the first free cell in the resulting array. By default, I equals J equals K equals 0. At each step, if both indices are in range I lesser than M and J lesser than N, choose minimum of A of I, B of J, and write it to C of K. Otherwise, go to step 4. Increase K, an index of the array, algorithm located minimal value by 1. Repeat step 2. Copy the rest values from the array, which index is still in range, to the resulting array. Example. Example for merge sorting. 54, 26, 93, 17, 77, 31, 44, 55, 20 are the unsorted array. At the beginning, the array would be divided, and at the end, the array is merged. The merging operation is shown in the figure. Complexity analysis. Merge algorithm's time complexity is O of n plus m. It requires O of n plus m additional space to store resulting array. Code snippets. The code snippets show how merge soft works. M minus size of A, N minus size of B, S size of C array must be equal or greater than M plus N. Conclusion. Thus we learned about graphs and the following in details. Graph representation, traversal schemes, spanning tree, shortest path algorithms, primes and Kruskal's.